Hello everybody, this is our first lesson after the Unit 2A exam, and this is a uniform circular motion. Uniform, as you remember, just means to be constant, so we have this constant circular motion. So think about planets spinning around the sun, or if you have a rock tied to a string and you're swinging the rock around your head. Those are examples, or at least they can be examples, of uniform circular motion. We need some special formulas for this unit, but there won't be a great deal of new equations, so I think that you'll probably revel in that. The bookwork associated with this lesson is right up here at the top of the slide. We're going to do questions 88 to 103. And our aim is how can we describe circular motion, especially in the ways that it's different than straight line motion or even two-dimensional motion. So I want you to pause the video and I want you to consider the answers to these questions. And once you come back, I will offer you some answers. So my explanation for the first question, which reads, which moves faster on a merry-go-round, a horse near the outside rail or one near the inside rail? My explanation involves this little diagram I just put in. So here's the top view of the merry-go-round, and this blue dot is the horse near the outside rail, and here is a horse near the inside rail. But in any case, the horse near the outside rail has to travel all the way around the outside of the circle to complete one revolution. And then, of course, the horse on the inside of the scale of the merry-go-round, it only has to go around the inside of the circle. And so, of course, it's just going through this smaller distance. So if the outside horse is covering a larger distance in the same amount of time, it's moving faster. Whereas if the inside horse is moving a shorter distance in the same amount of time, then it's moving slower. And I tried to show that right here by saying that you'll have a larger velocity if you have a larger distance. And on the other side, for the inside horse, I was trying to say that you'll have a smaller velocity if you have a smaller distance and a larger time. So that's my explanation for number one. Secondly, why doesn't the water fall out of a bucket when it is swung upside down? My answer to that one's pretty simple. The acceleration due to gravity is going to bring the water down. So if you can overcome that acceleration, or if you can cancel that acceleration, then the water will stay in the bucket. So I said offsetting the gravitational acceleration with circular acceleration, but we'll have a new term for circular acceleration really soon. All right, so lastly, if you swing a ball on a string in a circle over your head and the string breaks, how will the ball continue its motion? Draw a diagram. So here's my diagram of the ball being swung around. If the string were to break at this position, which we can call position A, then this is my symbol for break, not an X. So if the string breaks there, the ball at that moment was swinging in a, let's see, this would be a clockwise direction. So it's still going to be moving, generally clockwise, but it won't be following a circular path anymore. Newton's first law says that it will continue moving in the way it was moving when this force was removed. And therefore, it was moving, at this moment, it was actually moving in this direction. And if you waited just one moment longer, it would change direction because it needs to follow the path of the circle. But at this moment, just this one moment in time, it's moving this way. So if you broke the string at that moment, then the ball is going to take that path. We call that path a tangent to the curve, or you could say perpendicular to the radius. There are a couple ways of saying it. But just to make sure that you have that concept, let's take the ball over to position, we'll say over here, we'll call this position B. So if the ball were still moving in a general clockwise direction, and it had gotten over to position B, and that's when you break the string. Then, which way would the ball go? Pause the video and think about it. So the ball, if it was moving clockwise, when it reached point B and then the string was cut, then the ball would go this way. It would follow a path perpendicular to the radius, or you could say tangent to the curve, but generally it would continue the motion that it was experiencing at the moment that it was separated from the circle. So we've already begun to answer the question, how can we describe circular motion? But we're going to need to cover a lot more. So let's go to the next slide. So uniform circular motion is actually, in some ways, like Newton's first law. In fact, I mentioned it in the do now. And it's saying that an unbalanced force acting on an object will produce a change in the object's velocity. And what we need to consider at this point is that if you have a string or gravity or something that's pulling something towards the center of a circle, then that is most definitely an unbalanced force. And if we assume that that unbalanced force is only pointing towards the center of the circle, like the force is only going this way rather than, I guess what I'm saying is the force can't be going this way at all. There can't be any component of the force that's pushing it that way. It can be moving in this direction, but there can't be a force pushing it in this direction. All of the force, like the string or the gravity, all of the force needs to be towards the center. But if that's true, if all of the force is towards the center, then you will get a change in the velocity because you're changing direction, but you won't get a change in the magnitude of the velocity. So in other words, it won't speed up or slow down. I'm going to draw in, this was an animation down here in the bottom left, so I'm going to draw in my stationary version of what you would have seen. So there's my circle, and at this moment in time, the object it's definitely moving along this line, which is tangent to the curve, but its acceleration is all towards the center of the curve. And the reason for that is no mystery. It's because the force is towards the center of the curve, and the acceleration will line up with the net force. So if we let this ball move a little bit along its path, and we let it get to this position, we can also analyze where we think the V and the A, which direction the V and the A would be taking at that moment. So pause the video and consider which direction V would be and which direction A would be. So I just included my answer. The V, the velocity or the motion, is going to be perpendicular to the radius or tangent to the curve, and the acceleration will be towards the center. Take another moment, pause the video, and consider the direction that V would be and the direction A would be when the ball reaches this point in its path. If you were thinking this might be the case, you are correct. The velocity is going to be tangent to the curve and perpendicular to the radius, whereas the acceleration will point towards the center of the curve. And you guessed it, I want you to do the exercise one more time, but the ball has reached this point in its path. Pause the video and consider the directions of the velocity and the acceleration at that point. And if you got that as your answer, you are correct. Again, velocity is going to be tangent to the curve, perpendicular to the radius. Acceleration will be pointing towards the center of the circle. So when we describe the motion of the object, let's say that the motion of the object is circular, but also we can say that its acceleration is towards the center. So the motion, I suppose, is tangent to the curve at any moment, but the acceleration is always towards the center. So the acceleration tangent to the curve, that's going to be absolutely 0 meters per second squared, because tangent to the curve, it's in constant circular motion. So there's no acceleration tangent to the curve. But perpendicular to the curve, there is a force that pulls it towards the center, which causes an acceleration. So perpendicular to the curve, we have an acceleration which is positive, but it's also constant. So as opposed to tangent, there is an acceleration, but perpendicular to the curve, you have a positive constant acceleration. Oh, and it's always pointing towards the center. All right, so this slide's about centripetal acceleration. Basically, if you have any object that's moving uniformly in a circular path, the only way it can stay moving in that circle is if it is also accelerating towards the center. You could think about the moon revolving around the Earth for an example like this. So the moon is experiencing Earth's gravity, and it's going to have acceleration towards the center of the Earth, and that's the reason why the moon is able to move in a circle. Or in another way, the moon would not move in a circle around Earth if there were not an acceleration bringing it towards the center. So it's basically, if you have a force that's going towards the center of the circle, it'll produce an acceleration, and that's the reason why objects move in circles. So the equation that describes this is written here. So using this equation, AC equals V squared over R, this is an acceleration, so it's meters per second squared. This is velocity, so think meters per second. And the radius is akin to distance, so the unit will be meters. And then this question down here, it says, what's the relationship between mass and centripetal acceleration? I want you to base it on this equation. Pause the video for a second and think about an answer. If you were thinking that there is no relationship based on this equation, then you are correct. So no relationship mostly because there's no mass in this equation, so you can't draw a conclusion. Compare the time it would take each ladybug to complete a revolution. So I'm referring to these little ladybugs down here. And a revolution would just be one trip around the record as the record spins. But each of these ladybugs would take a different pathway. I'll highlight those now. So since the ladybug on the outside has to travel a much longer distance to go through this entire revolution than this ladybug, whose distance is going to be a much shorter revolution, they're doing it like in the same amount of time, but they're going different distances. So I'll give you a graphical representation of that. So the speed would be larger for the ladybug who's traveling the longer distance, but assuming that the times are equal. The speed would be a lot smaller for the ladybug that travels a smaller distance. So in essence, this ladybug right here, traveling the larger distance in the same amount of time, will have a greater average speed. But it would take them the same amount of time. So I'll write that in as well. And using information from this comparison, then we can compare their rotational speed and tangential speed. So rotational speed just means like how fast the record is rotating. And obviously all points on the record are rotating at the same speed. So at least rotationally, they're completing 360 degrees of rotation in equal time period. So that's going to give you the same rotational speed. But tangential speed is the V bar that we were looking at up here, meaning like it's the motion tangent to the curve. So those two are very different, and the ladybug on the outside has a larger rotational speed. So on this slide, we definitely have some vocabulary, which is that we have centripetal force. Centripetal force is a force that points towards the center of a circular path. And it also is responsible for causing the acceleration that would keep an object moving in a circular path. So on this particular diagram down here, we have FC coming in towards the center. We have another FC coming in towards the center. Basically, at any point that an object is, its force is going to point right towards the center. And that is the exact same answer as the acceleration. Both the force and the acceleration would point towards the center. Now I have a little pro tip for you. This equation's on your reference table, that AC equals V squared over R. And so is this one, the one that says that FC equals MAC. This is an adaptation of F equals MA. But in any case, if you take this equation and put them together, so that essentially you are just combining them so that it says FC, but instead of A, you're using just V squared over NR, you're going to get this equation. FC equals mv squared over r. So again, the v squared over r is replacing the A. So for this. So you get this equation. It's not on your reference table exactly because it is a combination of these two equations, but this one helps a ton for many different kinds of questions. All right, so let's answer some basic sort of conceptual questions. In which direction is force applied? Towards the center. Please remember that. In which direction does acceleration occur? Towards the center. The acceleration and the force will always match up. And what causes the object to travel in a circle? It's a center-seeking acceleration, or force. I guess you could say either one. All right, a little bit more on centripetal force. So as the force points towards the center of the circle, it does cause an acceleration. But that acceleration is only towards the center. When we're talking about this tangential motion, which is the actual speed or the velocity of the object, that is no acceleration at all in this direction. It's a completely constant speed. But in this direction, it is accelerating. So we can answer this question now, where we describe the object's velocity, centripetal acceleration, and centripetal force. Please pause the video and come up with an answer for each. So the velocity is represented by this section of the graph, and it is described as tangential, and it's also described as having constant speed. So not only is it tangential, but it's also constant speed. Acceleration, centripetal acceleration is going to be towards the center, but also constant. Not constant speed, constant acceleration. And FC is also going to be towards the center, and it's going to be constant as well. Now it's time for a math question. A 1.5 kilogram cart moves in a horizontal circular path of 1.3 meter radius at a constant speed of 2 meters per second. Calculate the magnitude of the centripetal acceleration of the cart. The best equation for this is the equation AC equals V squared over R. And I know that I am leaving out the mass that the question had, but this equation doesn't include mass, and that's okay to leave it out. So the V, the velocity, was the constant speed of 2 meters per second. Don't forget to square that, it's a V squared. And put it over the radius of 1.3 meters. I'll calculate that, and I'll be right back. I got 3.08 meters per second squared. All right, so the next question says, calculate the magnitude of the centripetal force on the cart. And the best equation for this is going to be FC equals MAC. And that's assuming that you trust your answer for AC, because I am going to use my own answer for AC. The mass is going to be used now. It's a 1.5 kilogram cart. And the AC that I just solved for was 3.08. So let me calculate that, and I'll be right back. I got 4.62. And this is a centripetal force, so it's going to be newtons. And I know that it didn't ask for this because it only asked for the magnitude of each of these questions. So it didn't ask for the direction, but in both cases, the direction would be towards the center, and that's for AC and FC. All right, so there is this other kind of force that people talk about, and it's called centrifugal force or centrifugal force. And it's different than centripetal force in a lot of ways. One of the ways is that they would be opposite. By their Latin roots, centripetal would mean center walking or center seeking, whereas centrifugal would mean center fleeing or center chasing. So that's the first major difference, is that instead of seeking the center, or instead of pointing towards the center, they would point away from the center. But the other major difference is that centrifugal force is fake. It doesn't exist. This is not real. But people talk about it all the time, like it's a real thing. And the reason for that is actually an issue of perception. So basically, I ask you to consider the instance of somebody swinging an object around their head. And we know after this lesson that the force actually points towards the center. But imagine now that you were actually inside this little can. So I'm going to put a little human being inside there. So if the human being is inside the can, you can put yourself right here as well. It's a top view. So that's another human being inside the can. If you were inside the can, what force would you feel? Would you feel like you were being pressed towards the outside of the can? Or would you feel like you were being pulled towards the center? Now we know in physics that we are being pulled towards the center. That's the reason why you're moving in a circle. But in terms of perception, do you feel like you're actually going this way? And I think most of you would say yes. Like most of you would feel like you would be pressed against the outside wall of the can. And that is just an issue of perception, because if you're actually being pulled this way, Newton's third law says that you'll exert an equal force that way. And that's what you're feeling. You're feeling both of those forces interacting as the wall presses against you. So in any case, if you need proof that centrifugal force doesn't exist, consider this example. So we have that same idea, but looking down from a top view, and the thing that matters now is that we're going to cut this string. So imagine the string is cut. And the person is absolutely convinced that he's being pressed this way. So I'm going to put the imaginary force, centrifugal force, this way. We can call it, I don't know, we'll just call it centrifugal force. I don't know a good symbol for it. But he feels like he's going this way. If centrifugal force were real, then when the string was cut, the man would fly this way because his acceleration would match the force. But that's how I know centrifugal force is fake. And that's because when I cut the string, the man does not fly this way. He doesn't go away from the circle. He does not. Instead, he goes this way, which is the way that Newton's first law would say he would go if the string were cut, because he would just continue with the motion, that tangential motion that he had at that moment. So in any case, centrifugal force is a real thing that people talk about, but it's not a real thing. At this point, we've reached the pair up. I'm just going to make copies of this, and we can work on this in class. And here's some more pair up. And here's a summary. I do want you to copy these questions down under classwork in your binders. It's a separate page from your notes. And I hope to go over these in class. So please remind me to do that. Thank you for listening to this lecture. I'll see you soon.